Look up at the night sky. See it, the moon? A constant presence in our skies, a source of wonder, of myth, of scientific inquiry. But have you ever stopped to ask, where did it come from? Unlike stars, which are born from collapsing clouds of gas and dust, planets and their moons have a more complex formation story. Most moons in our solar system are tiny compared to their host planets. Think about Mars's moons, Phobos and Deimos, which are basically just large rocks. But our moon is about 1/4 the diameter of Earth. That's a pretty hefty companion. Imagine the early solar system, a chaotic, violent place. A Mars-sized object, Theia, is on a collision course with Earth. The giant impact hypothesis hinges on this colossal collision, proposing that Theia slammed into Earth with unimaginable force. The early solar system was crowded with protoplanets, constantly colliding and merging. Theia is thought to have been one of these protoplanets, perhaps sharing Earth's orbital neighborhood. The collision vaporized a significant portion of both Earth and Theia, creating a massive cloud of superheated rock and dust. Theia slams into the young Earth, releasing energy equivalent to billions of atomic bombs. Debris, ejected from the collision, is flung into orbit around the wounded Earth. Gravity begins to exert its pull, and the debris field starts to clump together, forming our moon. As the cloud of debris cools and coalesces, a new dawn breaks for both Earth and the moon. The impact has tilted Earth's axis, giving rise to the seasons we experience today. The moon, too, bears the scars of its violent birth, with its surface pockmarked by craters. The Apollo missions brought back lunar rocks that provided compelling evidence for the giant impact hypothesis. The chemical makeup of the moon's surface is remarkably similar to that of Earth's mantle. This similarity suggests that the moon and Earth share a common origin. Isotopes are like fingerprints, unique to each celestial body. The isotopic fingerprints of Earth rocks and lunar rocks are practically identical. This similarity is difficult to explain unless they shared a common origin, supporting the giant impact hypothesis. The moon's relative lack of volatiles is a key difference from Earth. The impact would have generated immense heat, vaporizing most of the volatiles present in the debris cloud. This process, combined with the moon's weak gravity, explains why our celestial companion is so arid. Piecing together the moon's origin story is like assembling a giant jigsaw puzzle. The giant impact hypothesis stands as the best explanation we have so far. It's a story of cosmic violence and creation, giving birth to the familiar face that graces our night sky. The fission theory suggests the young Earth spun so rapidly that a chunk of its molten mass was flung outward, forming the moon. However, the theory quickly ran into problems with the energy required and the differences in composition. The isotopic fingerprints tell a more nuanced story supporting the giant impact hypothesis. Let's picture a different scenario. The early solar system, a chaotic playground of planets and protoplanets with gravitational interactions sending objects careening through space. The capture theory suggests that the moon formed elsewhere in the solar system, perhaps in a different region of the protoplanetary disk, and was later captured by Earth's gravity during a close encounter. It's a cosmic game of gravitational billiards with the moon as the ultimate prize. This theory has the advantage of accounting for potential compositional differences between the Earth and the moon. After all, if the moon formed elsewhere, it could have a different chemical makeup. But the capture theory, like the fission theory before it, stumbles when it comes to the finer details. The biggest challenge is the sheer improbability of such a capture event. For the moon to be captured by Earth's gravity, it would have to be slowed down just the right amount at just the right distance. Too fast, and it would have zipped past Earth and continued on its merry way. Too slow, and it would have collided with our planet, with catastrophic consequences. Even if we grant the possibility of such a delicate gravitational dance, the capture theory struggles to explain the moon's nearly circular orbit. Captured objects tend to have highly elliptical orbits, a testament to their chaotic past. The moon's orbit, on the other hand, is an anomaly, a whisper of a more orderly formation process. Now let's imagine a more harmonious beginning for the Earth-Moon system. The co-formation theory proposes that the Earth and Moon formed together side by side from the same swirling cloud of gas and dust in the early solar system. It's a story of cosmic companionship, of two celestial bodies emerging from the same primordial soup. This theory has the appeal of simplicity. It explains the Earth and Moon's proximity to each other. After all, they were formed in the same region of space. It also accounts for the Moon's relatively large size compared to other moons in the solar system. If they formed together, they could have accreted material from the same region of the protoplanetary disk. However, the co-formation theory falters when it comes to explaining the compositional differences between Earth and the Moon. If they formed from the same cloud of material, their compositions should be nearly identical. But as we've seen, there are subtle but significant differences, particularly in the abundances of certain elements like iron. Furthermore, the co-formation theory struggles to explain the Moon's unusual orbit. If they form together, their orbits should lie in roughly the same plane, but the Moon's orbit is tilted relative to Earth's orbital plane, a discrepancy that hints at a more complex formation history. We've explored theories for the Moon's origin, fission, capture, and co-formation. None fully explain the evidence. The giant impact hypothesis shines here. It explains the Moon's similar isotopic composition to Earth's mantle. The Moon's lower density and lack of volatiles are due to the intense heat from the impact. Computer simulations support the giant impact hypothesis. It remains the most compelling explanation for the Moon's origin. The Moon's formation is a tale of cosmic violence and celestial rebirth. The Moon, our celestial companion, is more than just a pretty face in the night sky. It's a key to understanding our planet's history, reflecting events from billions of years ago. By studying the Moon, we gain insights into the early solar system and Earth's formation. Imagine Earth 4.5 billion years ago, a molten cauldron after the Moon's birth. This period, called the Hadean, was marked by intense heat and asteroid bombardment. The Moon's craters provide a window into this chaotic time. Studying lunar craters helps scientists understand early solar system impacts. The Moon's unchanged surface preserves a record of past events. It's like a cosmic time capsule, revealing Earth's turbulent youth. The Moon's influence on Earth extends far beyond its role as a celestial timekeeper and a source of romantic inspiration. It's the primary driver of our planet's tides, a rhythmic ebb and flow of ocean waters that has shaped coastlines, influenced marine life, and even played a role in the evolution of life itself. Tides are caused by the gravitational pull of the Moon and, to a lesser extent, the Sun. Because the Moon's gravitational force is stronger on the side of Earth facing it, it pulls the water on that side towards it, creating a bulge. A corresponding bulge occurs on the opposite side of Earth due to inertia, as the Earth is pulled towards the Moon more strongly than the water on that side. These bulges, aligned with the Moon's gravitational pull, create high tides. Low tides occur in the areas between the bulges. As Earth rotates on its axis, different locations experience these tidal bulges, resulting in the daily cycle of high and low tides we observe. These tides, while seemingly simple in their mechanics, have profound implications for life on Earth. They create a dynamic intertidal zone, a constantly changing environment where land meets sea, fostering unique ecosystems that are home to a diverse array of plants and animals. Tides also play a role in driving ocean currents, which help regulate global temperatures and distribute nutrients throughout the oceans. Beyond its influence on our oceans, the Moon plays a crucial role in stabilizing Earth's rotation. Our planet, you see, is not perfectly spherical, nor does it spin on a perfectly straight axis. It's slightly flattened at the poles and bulging at the equator, and its axis of rotation is tilted at an angle of about 23.5 degrees relative to its orbital plane. This tilt, responsible for the seasons we experience, is subject to wobbles and variations over long periods due to gravitational interactions with the Sun, Jupiter, and other celestial bodies. However, the Moon's gravitational influence acts like a steadying hand, a cosmic anchor that helps dampen these wobbles and maintain Earth's relatively stable axial tilt. This stabilization is crucial for life as we know it. Without the Moon's influence, Earth's axial tilt would be subject to more extreme variations, leading to dramatic climate swings that could disrupt ecosystems and make it difficult for life to thrive. The Moon's presence, therefore, has played a silent but vital role in creating the conditions necessary for life to flourish on our planet. The Moon's stabilizing influence also has implications for the length of our day. Tidal interactions between Earth and the Moon cause a very gradual slowing of Earth's rotation, a phenomenon known as tidal braking. Over millions of years, this braking effect has lengthened the Earth's day from an estimated 5 hours during the Hadean Eon to our current 24-hour cycle. The story of the Moon's formation isn't just about understanding our own backyard. It has implications for the search for life beyond Earth. As we discover thousands of exoplanets, planets orbiting other stars, we're beginning to realize that our solar system, with its unique configuration of planets and moons, might be the exception rather than the rule. The giant impact hypothesis, if it holds true for other planetary systems, suggests that giant impacts might be a relatively common occurrence during planet formation. These impacts, while destructive, can also be creative, leading to the formation of moons, altering planetary orbits, and even delivering water and other volatiles to otherwise dry worlds. Understanding the role of giant impacts in shaping planetary systems is therefore crucial for assessing the habitability of exoplanets. A planet that has experienced a giant impact, for example, might have a different atmospheric composition, a more tilted axis, or a larger moon than a planet that formed in a more peaceful environment. As we continue to explore the cosmos, the Moon, our constant companion, serves as a reminder of the dynamic and often violent processes that have shaped the universe we inhabit. By studying the Moon, we gain insights not only into our own planet's history, but also into the vast tapestry of planetary systems that populate our galaxy, some of which might harbor life as we know it, or perhaps life as we've never imagined it. The Moon, our celestial dance partner, continues to captivate and inspire us. Armed with science, we unravel its true story, as dramatic as any legend. The giant impact hypothesis helps us piece together our solar system's history. Evidence from lunar rocks and gravity points to a cataclysmic past. A Mars-sized object collided with Earth, creating our Moon. This impact gave birth to our Moon, influencing tides and stabilizing Earth's rotation. The Moon's formation reminds us of the dynamic universe. It's a story of cosmic violence and creation. But the story doesn't end there. The Moon is now a prime target for future exploration. New missions will uncover more clues about its formation. The quest to understand the Moon's origin isn't just about satisfying our scientific curiosity. It's about understanding our place in the cosmos. The Moon's story is inextricably linked to our own, a testament to the fact that we are children of the stars, formed from the same cosmic dust. As we delve deeper into the mysteries of the Moon, as we analyze its rocks, map its surface, and search for signs of ancient water ice, we're learning about ourselves, about the forces that have shaped our planet and ultimately our very existence. The Moon, once a distant object of wonder, is now within our reach, a destination for future explorers and a potential source of resources as we venture further into space. It's a stepping stone to Mars, a testing ground for technologies that will one day carry us to the outer planets and beyond. And as we stand on the lunar surface, gazing back at our blue planet hanging in the black void of space, we'll carry with us the knowledge that our presence there, our ability to unlock the moon's secrets, is the culmination of billions of years of cosmic evolution, a journey that began with a cataclysmic collision and continues to unfold with every new discovery. The moon, our celestial dance partner, invites us to continue exploring, to keep asking questions, to never stop marveling at the wonders of the universe we inhabit. It's a journey that takes us from the familiar face in our night sky to the very heart of our cosmic origins, a journey that reminds us that we are all connected, not just to each other, but to the vast and awe-inspiring universe that surrounds us.